This tutorial will explain the Curry-Howard correspondence in a more pedagogical way, more easily understandable and more intuitive. This is a complement to part 3 of chapter 3 of my functional programming tutorial, where I also talked about the Curry-Howard correspondence. In that chapter 3 I gave also exercises. In this tutorial there won't be any exercises. This only serves to explain things better and in more detail and in a more understandable and intuitive way. The main focus of the Curry-Howard correspondence is to make a connection between types in functional programming languages and logic derivations in the formal logic. And then the goal is to use the knowledge that we have about the formal logic to make some conclusions about how to write programs. So the goal of my tutorial is to show practical use of this theoretical knowledge. Let us begin with what types are available in functional programming languages, because it is that specific kinds of type constructions that is the basis of the Curry-Howard correspondence. Without these type constructions, it would be impossible to make a connection with logic and to use the mathematical knowledge that logicians have obtained. So what are these type constructions? There are the tuple, the function type, the disjunction, or also called the sum type, the unit type, and the possibility of having type parameters. This is my short notation for these types, for these type constructions. This is not syntax of any specific programming language. This is just a short notation I use to reason about types. Now, in all the functional programming languages that are in wide use today, such as OCaml, Haskell, Scala, F#, Swift, Rust, and so on, including more advanced and more experimental functional languages such as Idris and Agda, all these languages have the same type constructions that I just listed, up to the differences in syntax, of course. Their syntax is different, but once you understand how these types work in one of these languages, you basically understand how they work in all of these languages, because they work in the same way. Here's a Scala syntax for these type constructions. In order to understand how they work, well, I assume maybe you already know how they work, but even if you don't, it is important to see what are the expressions that are available in the language that have to do with these types. What can you do with these types? So let's begin with the tuple type. This is the Scala syntax for the tuple type. You can create a tuple type. In other words, you can create a value of the tuple type using this syntax. In order to create a value, you just take, let's say, two values, one integer, one string, and put them together in a tuple like this. This is the Scala syntax for the tuple value, and this is the Scala syntax for the type expression that is describing this value. So each language has a specific syntax for this. And with this syntax you create a new value called pair, which is equal to this, and it has this tuple type, integer and string. And in the short notation, this is how I denote it. Once you create a value of the tuple type, how can you use it? Well, the only way you can really use it is to extract some parts out of a tuple. So you can extract the first part, or you can extract the second part. In the Scala syntax, this is how you extract parts of the tuple. And here, for instance, you can now compute a new value called y, which will be of type string because the second part of the tuple is of type string. In Scala, the type annotations are not required. In many cases, you can just omit them from your code. But I will write them just to be clear what the types are of the values we're creating. So these are the two basic things you can do with the tuple type. You can create a value of the tuple type, and you can use an already created value. We will do the same kind of reasoning about other type constructions now. We will see how they are created and how they can be used. So the function type, consider as an example, a function that takes an integer argument and returns a string value. This is the syntax for this kind of function in Scala. One of the possible ways of defining this function is to write this expression. This is the function expression, which is the function itself. It takes an argument named x, which is of type integer, as we just said here. So you do not have to repeat the integer type annotation, but you could if you wanted to be more verbose. So you say this is a x, the name of the argument of the function, then you write this arrow, and then you write the expression, which is the body of the function. This expression will be computed and returned when the function is called. So this expression uses this x in some way to compute a string value. How do we use the function? So here we created a function value of this type. You could actually also say val_f instead of def_f in Scala. But Scala has certain limitations, and sometimes you have to say def, especially when the function has type parameters. You cannot say val, you have to say def. These limitations are unimportant for the purposes of this tutorial. So we will just consider this as a value of this function type. So functions are still values in Scala and can be used as values, even though sometimes you have to say def and at other times you can say val. Having created a function of this type, how can we use it? Well, we can only do one thing really with a function. We can apply the function to an argument. The argument must be of type string, of type integer, because that's the type of the function. The first thing here is integer, so it means that the argument of the function must be of integer type. So we put some integer value here, we apply the function to this value, and the result is a value of a string type. And so that's how you use a function. Disjunction type is another important type construction. In Scala, it is defined in the standard library as the either type. It has two type parameters. So either with type parameters int and string, and this is the syntax for type parameters in Scala. So either is a type that represents a value that can be integer or string. Let's see how we use these types and how we create them to understand how they work. To create a value of this type, we can write things like this. So here's x, which has this type. This is the value that x has. In the standard library, the disjunction of integer and string is defined with either, and it has names for the left part of the disjunction, which is left, for the first part of the disjunction, and for the second part of the disjunction. The name for that is right. So these are labels or names that are required in Scala. So you cannot have a disjunction like this without names. So the standard library defines the disjunction called either, and its names for the first part and for the second part are left and right. And this is then the syntax that you use to create values of a disjunction type. So x is a value of this type, and it contains an integer inside, labeled by this name left. And y is also a value of this type, and it is containing a string inside, and it's labeled by the label right. So this labeling allows us to distinguish which part of the disjunction it is, and the labels are required. Every time you create a value of this type, you must give the label. And once you give the label, then the value inside this label must be of the right type. So for left, it's the integer. For right, it's the string. Once you have created a value of the disjunction type, how can you use it? Here's what you can do. You can match on the disjunction, and the match contains two cases. It can be a left, and then you have the value which was in the left, and you can write a function body that will use that value in some way and compute some other value, let's say Boolean value. The second case is that you have a right label. So in this case, our example does not actually need to use this value, so the syntax is to write underscore, meaning that we do not need to use the value what is inside the disjunction part with this label. But we could have a different example where this could be, let's say, x, and this could be some expression using x to compute a Boolean value. So this is a match expression, or a case expression, sometimes called. And this is the way you can use values of disjunction type. So to create them, you have to specify which label you use, so you can either create a left or the right. There's no other way to create values of this type. And once you have a value of this type, you can use a match expression with several cases so that you decide which part you were given and do appropriate things in each case. And notice there is no way to create a value of the either type where you don't know whether it's left or right. When you create it, you must know. When you are using it, then you don't know, because somebody gave you this and they created it, but they don't tell you which one they created. So then you use the match expression to find out. That's how you work with disjunction types. The final construction is the unit type. The unit type is denoted with this syntax. It looks like a tuple with no elements inside, tuple with 0 parts, or an empty tuple. Because tuples could have 1 part, 2 parts, 3 parts, and so on, each part having some specific type. So it could be a tuple of integer, string, Boolean, whatever. But here, it looks like a tuple with 0 parts, an empty tuple. So this type only has one value, the empty tuple value. There is nothing that you can write in there, and there's only one way to write that. So this is a very interesting type that only has one value. And so you can create it by just writing this empty tuple expression, and the result will be a value x of this type, which is called unit in Scala. And there isn't really any way to use it, because there is nothing inside it. There's no value that it holds inside, it's empty. So you could pretend that you're using it if you have a function that takes this type as argument. But actually, there's only one value of this type, and you can always create it if you need it. So it is kind of useless to say that you are requiring an argument of type unit and you're using that argument. You could require it, but you don't have to use it. There's nothing to use. There's no content inside it. There's just one empty value always. And so that means we only have one construction with this type, one kind of expression that can be written. Whereas all other constructions that had two expressions, one for creating, or actually one or this had more expressions for creating, and for using, we also have here more than one expression. We could take the first element or the second element. So all these constructions have some expressions that create values of this type and some expressions that use values of this type or consume values of this type and give you values of some other type. But for unit, there's only creation. There's nothing you can deconstruct here or extract out of it. Now, I gave you examples in Scala because that's the language I'm most familiar with right now. But exactly the same constructions are present in other functional programming languages. For example, just for illustration, I'll show you the same things in the OCaml syntax. The tuple type in the OCaml syntax is denoted like this, very similarly to my short notation, except for this star symbol. Instead of Scala's val keyword, in OCaml you use the let keyword. Otherwise, things are exactly the same in OCaml for creating a tuple. And using a tuple is slightly different. There isn't _1 or _2. Instead, there are functions first and second, so the FST and SND. And these are defined in OCaml's standard library. The function type is denoted like this. To create a value of the function type, you have to use the keyword fun, which is function creating keyword. Then you write a variable name or one or more. And then you write this arrow, which is different from the Scala arrow. Scala arrow is double arrow. And the OCaml arrow is a single arrow. Other than that, it's very similar. And then you have the body of the function. To use a function, you apply it to an argument. Now, in OCaml, applying function to an argument can look like this. In Scala, it requires parentheses around the argument. In OCaml, parentheses are optional. You can write them, but you can also omit them. So if you omit parentheses, then you just write space. And that's the syntax that people sometimes prefer. Also, look at this function body. It doesn't have any parentheses. It applies this function to this argument and to this argument. In Scala, the analogous syntax would be that you have to put parentheses around this, would be one set of parentheses, and then you also have to put parentheses separately around this. So this syntax is less verbose than the Scala syntax, but the Scala syntax is more familiar to people used to mathematical notation, where functions are applied to arguments, usually with parentheses. Although in mathematics there are certain cases when this is not done. For example, cosine of x usually is not written with parentheses. It's written usually without parentheses. Like function, if this were cosine, and this were some value, this would be similar to mathematical notation. But mathematical notation does not use functions with more than one argument, or more than one sets of arguments. Scala does, OCaml does, functional programming languages usually do. And so the syntax becomes then again unfamiliar. Anyway, this is just syntax. It's easy to get used to syntax. A couple of weeks of work and you're not noticing the syntax anymore. Syntax is superficial. It is the meaning, the semantics that is important. And the semantics is the same. Use function by applying it to the argument of the correct type, and you get the value of the correct type. Disjunction type in OCaml is defined using this syntax. Scala also has a syntax for defining the disjunction type, but it's much more verbose than this. So I did not write it. It's the case classes syntax. Sealed trait in and case classes. Very verbose, so I did not want to write it. It will be familiar to Scala programmers. In OCaml, this is the syntax where you say you define a new type, E, and this type is a disjunction. It has two parts. The first part is labeled with the word left, which is the name of this part. Of is a keyword. Int is the type that it contains. The second part of the disjunction is labeled with right as the name. Then of is again the keyword. And then string is the type that it contains. You create values of the disjunction type using this syntax, again very similar to Scala, except for keyword let, and except for the absence of parentheses. So here it looks like you're applying a function to the argument, just like here it looks like you're applying a function to the argument, and here you do it without parentheses. Otherwise it's exactly the same. So you can create a left value or you can create a right value, and the left value must contain an integer and the right value must contain a string. Once you have a value of disjunction type, you can analyze it by using a match expression. In OCaml syntax it looks like this, very similar to the Scala, except for slightly fewer parentheses and fewer keywords. Other than that, very similar. You have a left case and the right case, and these are functions. They look like function from I to I greater than 0, function from ignored argument to false. So a match statement is basically taking your value of the disjunction type and two functions. Depending on which part of the disjunction this is, you use one function or you use the other function to compute the result value of the type bool. And the unit type in OCaml, it's exactly the same in Scala. You have two functions and you match on the disjunction. Unit type, exactly the same. Haskell syntax is even less verbose than OCaml. Other than that, it's exactly similar. Usually in Haskell, people do not write types after they define variables, and there's no keyword necessary. There's no val or let usually necessary in Haskell. Other than that, it's very similar. This is the pattern matching syntax that extracts the second part of a pair. And y after this definition becomes a string value. Function type, very similar, except for the very short keyword, which is this backslash, that replaces the fun keyword or def keyword in Scala. In Haskell, this is the backslash keyword. And then you write your argument name, your arrow, and the function body. The function body uses notation without parentheses and with infix syntax. So ++ is the operation of concatenating the string with this string. Show is a standard library function that takes an argument and gives you a string out of it, similar to Scala's .toString. You use this syntax to apply functions to arguments in Haskell, just like OCaml. Parentheses are optional. This is the syntax for defining the disjunction type, very similar to OCaml, except there are no keywords of necessary. So very similar, less verbose than OCaml. otherwise very similar. You create values of disjunction type and you match them in a case expression, which is exactly similar to the match expressions in OCaml and Scala, using two functions that compute the Boolean value in the two cases. And the unit value is like this. So you can see all three languages have very similar type constructions, and this is why what I'm going to present right now applies to all of these languages. There's no difference at this level between these languages. They are the same. Once you understand one of them, you understand others. At least you understand how to work with these types and how logic helps you work with types. That understanding is universal, and I'm pretty sure if there are further languages invented, they will still have the same constructions that I listed, and the understanding will persist because the mathematical value is so great. And I will show why mathematical value arises here. It arises if we consider propositions that correspond to types. So how do we do that? What are these propositions that correspond to types? Let us define these propositions. Consider in the Scala syntax some variable that you define in your program, in your expression somewhere. Programs are expressions. So I will say program or expression. It's similar, the same thing. If in your program somewhere you have this, it means, assuming of course, it means that you can compute a value of type t at some part of your program, assuming of course that your program compiles and runs correctly. So this is the proposition that corresponds to types. The proposition is that your code can compute a value of this type. Any value, some value, doesn't matter which value. The proposition doesn't know which value you have computed. All it knows that you have computed some value of the type t, for some type t. Let's denote this proposition as ch of t. So mnemonically, this is code has a value of type t. Again, we don't know which value it is, and at this level we do not express that. We don't say which value we have computed. We just know that we have computed a value of this type. This proposition can be true or false for certain programs, depending on the program, because some programs may be unable to compute certain types because they're not given some data from which to compute these types, and other programs are given that necessary data. So these propositions could be true or false, first for different types, and second for different programs. So let us now see what type constructions we have, and what are the propositions that correspond to these type construction. So for type variable t, the proposition will be denoted as ch of t, and in the short notation I will just write t, meaning this at the same time the type and the proposition, because as we will see, there's a one-to-one correspondence between types and propositions. Well, we just defined it. We just defined the proposition that corresponds to any given type. So I will use this notation as a short notation both for types and for propositions. But for clarity, I will sometimes write ch of t, just to make it clear what we mean. Consider now the tuple type. The tuple type means that somewhere in your program, let's say, you have computed a tuple value. Well, it means that you have computed the integer, and also you have computed the string. There's no other way to compute a tuple value. You have to compute both parts of the tuple, or all the parts of the tuple, if there are more than two. So if you have a tuple AB, and you have computed the value of this type in your program, it means you have computed a value of type A, and also you have computed the value of type B, some value of type B. So CH of the tuple AB is CH of A and CH of B as propositions, where AND is the logical AND, logical conjunction of propositions. In the short notation, the logical conjunction is denoted like this in the standard logical notation. I will also use this notation for reasons I'll explain in detail below. Now let's consider the disjunction type, the either. If you computed the value of either, it means you computed a left or you computed a right. You must have computed one of these two. So in the logical proposition, it means that CH of either AB is equal to CH of A or CH of B, where OR is the logical OR. It is a disjunction operation in the logic, which is usually denoted like this in the logic, but I will also use this notation for disjunction, for types especially. Function type means that you have a function that computes B given A. It doesn't really mean you have an A or that you have a B. You don't necessarily have any of these two, but if someone were to give you a value of type A, then you would be able to call this function and compute a value of type B. So the proposition CH of A to B, I'm reading this function type as A to B. So CH of A to B is the logical formula that is if CH of A, then CH of B. So if I am able to compute CH of A, then I'm also able to compute CH of B. So this is a logical implication. And the short notation for that will be this. The unit type can always be computed. It does not need any previous data for it to be computed. We can just always write this expression at any time. And so the proposition CH of unit is a proposition that is always true. Any program can compute unit type expressions. So this corresponds in the logic to a proposition that is identically true. It is always true in all programs. In the short notation, I will denote this as 1, the symbol 1. So this is already very interesting. It shows that each of the type constructions corresponds to a logical construction or a logical operation, logic operation. If we consider the propositions defined by this. A couple of more remarks for especially since we're going to use type parameters a lot. In Scala, the type parameters are denoted like this. And if you have a type parameter, it means on the logic that something is asserted for all t. So some propositions are considered for all types t. Here's an example. If you want to define this function in Scala, duplicate, it is parameterized by parameter a, which is any type A. So A is a type parameter variable. And for any type A, the function takes an argument of type A and returns a tuple of A and A. It is clear how this function could be implemented. Just takes some x of type A and returns a tuple of x, comma, x. Now the type of this function in the short notation would be written like this. And in the logic, it would correspond to this formula. For all A, from A, if A is true, then A is true and A is true. because the tuple corresponds to the logical and, the conjunction. Now, this statement, that for all A, it follows from A is true, that A is true, and also A is true, that is certainly true in the logic. It's not a very interesting statement, but it is certainly a correct, true statement, or in other words, a theorem in the logic. So it's very interesting that functions that we have here correspond to theorems of logic. How do we understand this? So what are the logical relationships that we have between these CH propositions? These propositions show that we can compute certain values of types that are given. Logical relationships between these propositions mean that we can see that if a program can compute a value of one kind of type, then it can also compute a value of another kind of type. So that would be a logical relation or relationship of entailment between propositions, and that's what logic usually studies. So if we understand purely on the logical side how to derive one proposition from another, we will be able to make conclusions about programs, about what kind of types can be computed if some other types are given or can be computed. So in logic, these relationships are studied through purely formal means. You lay down axioms and derivation rules of a logic, and you follow them. For us, though, all these logical relationships are direct expressions of the kinds of code that you can write. So that is the second side or part of the correspondence of the Curry-Howard. Code corresponds to proofs or derivations in the logic. So we will explore this now in detail. In logic, we are reasoning about what follows from what using something called a sequent. So sequent is a device used by logicians to denote an elementary task of proving something when assuming something else to be true. This is a notation for sequent. It has this symbol which is called the turnstile. To the left of the turnstile are some logical formulas which are the premises. To the right of the turnstile is a logical formula which is the goal. So sequent in logic represents a proof task, that is the task of proving G, the formula G, or the proposition G, assuming that these premises are already proved. And the proofs in logic are achieved by using axioms and derivation rules that have to be specified in advance. Axioms in this notation would mean that we have a list of sequents that are already true by themselves, that do not need any proof. And derivation rules would mean a list of rules saying that a certain sequent would be true or would be derived if certain other sequents are already derived previously. So these are the rules of derivation. Which sequent can we derive given that some other sequents are already proved? So in order for us to be able to reason like this, we need to specify what are the axioms and what are the derivation rules that represent the logic of CH propositions, or as I call it, the logic of types. To make connection with our code, we need to translate our code fragments into sequence somehow. What we will do is that we will look at every construction in the code and we will see what kind of sequent represents that construction. So we will represent expressions by sequence. How excuse me. How does that work? A sequent like this would represent an expression of type C that uses some variables or parts or expressions of types A and B. So those are assumed as given, and out of those we build a new expression that has type C. Here are some examples using the Scala syntax. If we consider this expression where I added the type for clarity, in Scala you don't necessarily have to do this. So we compute the string representation of some integer and we append the string ABC to it, just as an example. Now, this entire thing is an expression of type string, but it uses a variable of type integer. So the sequent that represents this expression would be this sequent. The premise is the integer, which is this, and the goal is the string. So notice we are representing types of sub-expressions, so the sequent calls our attention to the fact that this expression uses an already computed value of type int, so this value should be already computed somehow previously. And then, so this becomes the premise of the sequent, and then we can compute a value of type string, so that is the goal of the sequence. So I'm not writing ch here just for brevity. If I wanted to, that would be here ch of int to the left of the turnstile, and this would be ch of string to the right of the turnstile. Another example is this expression in the Scala syntax. This is a function that takes an argument of integer type and returns this computation, which is a string. It's a string type. So notice this is the same expression as was here. Now it is used as the body of the function. Now this entire expression doesn't actually use any variables from outside. It has the variable x, which is the argument of a function. So this is a bound variable. It does not have to be computed before in order for us to have this function. So this entire expression has type integer to string. It has the function type. And it is represented by this sequent. To the left of the turnstile, there's an empty set of premises, because this expression does not use any variables that are previously computed. To the right of the turnstile is the function type. Again, more precisely, this would be ch of int to string. A very important remark here is that sequents only describe the types of expressions, the types of parts or variables that we're using. Sequents do not describe the actual computations entirely. So nowhere here does it say that we are actually taking this integer, converting it to string, and appending some other string to it. The sequent does not express this information. It only describes the types. It is focused on what is the type of the entire expression, which is the goal of the sequent, and what are the types of variables that are assumed to have been already computed, which is the premise of the sequent. Now, we can translate all the constructions that we had in functional programming languages into the language of sequence. And if we do that, which we will do in this slide, we will obtain all the derivation rules for the logic of types, as well as all the axioms. Each type construction that we have seen before corresponds to either a sequent or a derivation rule. The expression for creating it and the expression for using the type construction, they both give rise to some sequence, because we can just describe these expressions in terms of sequence. And so this sequence, for example, would assume that the function f has been already computed and that this number has been already computed. So that would be the sequence that has these two as premises and this type as the goal. So if we translate all of those constructions into the language of sequence, here's what we get. For the tuple type, the expression that creates the tuple type gives rise to this sequence. From AB follows A times B, because the expression is this, and it already uses the previously computed or available expressions of these types. Similarly, when we use a tuple, we assume that the tuple value has been already constructed, and then we obtain the value of the first part of the tuple or the second part of the tuple. So these sequences directly correspond to code fragments or to expressions of the code. They do not need a proof. They are axioms. For the function type, we have an interesting situation that the function type requires a body of the function to be created. So the body of the function needs to be already an expression that must have been possible to write. And so this expression is another sequence that we must already somehow have established that it can be written. Sorry, I'm here. So if I have this sequence, which is the body of the function that uses some variable of type A, then we can put this variable outside. So we have this body, we can put this x outside and make a function that takes x and returns this body. This construction of the language is represented by this derivation rule. If we have this sequence, which is the body, if we can write the expression for the body, then we can write the expression for the function. Using the function means applying it to an argument. So if we have an expression of this type, which is a function already somehow created and computed, if we have a value of the argument type, then we can compute a value of the result type. The expression for this is the application of function to an argument. And as I said, sequences do not say how this is implemented in code, but we need to keep that in mind. We need to keep in mind that each sequence that is proved really means that we are able somehow to write code representing these types as the sub-expressions or variables, and this as the type of the entire expression. For disjunction type, we have two possibilities to create. Two possibilities of creating a value of the disjunction type: inject into the left or into the right. So these are represented by these two sequences. And by writing this sequence, we represent the match expression, which takes a value of the disjunction type. It takes two functions, from A to some C type and from B to C, and the result is an expression of type C. So the match expression is always of this kind. We have new type C that is being computed in each case, and each case is a function from the value that is held by the disjunction to that new type. So we have to assume that we already computed this expression and we already have somehow these two functions, and only then we can produce a value of type C. So this is this sequent. And the unit type is represented by this sequent. It has no premises and it already can give us an expression of unit type. In addition to these constructions that use some specific types, we have constructions that are general. They're not using any specific types, and these constructions are in some sense trivial. They're very simple and obviously reasonable, independently of a programming language as well. Although we should note that everything we have done here is common to pretty much every functional programming language. So this is really not about a specific language. This is about functional programming paradigm as such. So what are these additional constructions? Well, one trivial construction is that if you have a value of type A, let's say x of type A, then you can just write x, and that's a valid expression. And that expression obviously has the same type A. So that is represented by this sequent. From A follows A. Or we can compute A if we have an expression of type A already. So that is kind of a trivial expression, but nevertheless we have to include this into the rules of our logic for completeness. This is the simplest expression we can write that is in some way using a given value. Another rule is that when we can compute some value of type G, given, let's say, some data, A and so on, then we can also compute G if we're given some more data, some additional data. We will just ignore that additional data because we can already compute G using these, and these are still here. So it's easy for us to compute this G. We just ignored this extra information that is given. We will have a lot of situations when we need to talk about sequence with a certain number of premises which we don't need to use explicitly. So we will denote them by the uppercase gamma. So that is a typical notation for a sequence of 0 or more arbitrary premises that we will not have to notate one by one. Finally, another rule is that the order in which data is given does not matter. So the same things can be computed if we have expressions gamma, which stands for any number of expressions, and then A and B, and also gamma, B, and A. So if we change the order in the sequence of premises, we can still compute the same goal. Well, this is kind of trivial too. It doesn't matter in which order you give parameters in a function, you can still rewrite the code in a trivial way or rename the variables and you get the same computation. So these are the additional rules. In what follows, we will use syntax conventions that are these. So first of all, the precedence of operations. So the implication associates to the right, which means that this expression means always this. And these parentheses don't have to be written. If we want first implication from A to B and then implication from that to C, then we will always write parentheses around this first implication. But parentheses around the second implication can be omitted. Another syntactic convention I'm using is that I will write types like this. What I mean by this is that the conjunction has the highest precedence, then comes disjunction, and then comes implication. So I would put parentheses like this if I wanted to completely specify the order of operations, but for brevity I will just write it like this, which agrees with the ordinary rules of school algebra, where plus has lower precedence than multiplication. Final important remark here is that we are talking a lot about A, B, and C and such propositions or formulas. What we actually mean is that these things are valid for all A, for all B, for all C. So we always imply that there is a for all in front of the entire expression with every variable that we use. In mathematics, this is called a universal quantifier. And so we will say all our variables implicitly, by convention here, are universally quantified. So when we write a formula like this, what we mean is actually that outside of the entire expression, there are quantifiers, universal quantifiers for each variable. So our statements are true for all A, B, C, and so on. So now we have all the axioms and all the derivation rules that govern the logic of types, as I call it. In other words, the logic of propositions of the form ch of something. So those are the Curry-Howard images of types, the propositions of form ch of something. What are the theorems that we can derive in this logic? Well, here's an example theorem and an example of how we would have to derive it if we are using these rules. We need to start with an axiom. So let's start with this axiom. This is a sequence that does not need a proof. This was this sequence, one of our rules. Now, by another rule, we can always add an unused premise. So this is this other rule. So if this sequence is true, then we can always add some new unused premise if we want. So let's add a premise B. And we have this sequence. So we already proved that this sequence is valid. Now we use the create function rule using B and A. So the create function rule says if we have something that has premise B and the goal A, then we could put B on the right hand side, and so this rule can put, so here's A on the left and B on the right. We can always rename that. So whatever's on the left, we can pull it to the right and make it into a function. So that premise will be removed from the list of premises and put it into the goal as a function. So then we do that and we get this sequence. We remove the premise B from premises, put it to the right, and we have this sequence. Now we do the same with A and this. So finally we get the sequence where A is pulled to the right and B to A was here before. So now we have this sequence with no premises and the goal is A to B to A. And we have proved this sequence because we have derived it using axioms and the rules of derivation. And since this is a formula that is derived from no premises, it is a theorem. What is the code that is behind this proof? Now, recall that every time we use an axiom or a rule of derivation, that corresponds to a certain expression of code that we could write immediately. For example, here, this axiom represents the expression x. Now, in my notation, I put the type as a superscript, just to be shorter and more readable. So this means I have, so this in Scala syntax would be written like this. X of type A. So I'm writing it here in a short notation like this. This expression uses X, and so it is represented by this sequence. The unused premise B means that we have some variable y, let's say, of type B. The create function rule means that we just put this, whatever was on the left, we put it to the right of the sequence, we make that into a function argument. So we just write an expression like this. We can always do that. If we have an expression for the body that uses some variable, we can always write this in front of that body, and we have a function expression. So this is how we implement the create function rule. So that will give us this expression. Now the second, and this expression still uses x, because this expression doesn't say what x is, so x must be already defined. And this is why this expression corresponds to this sequence. It has a premise of type A, which corresponds to this x of type A that has been already somehow defined outside. The second create function rule puts the argument x in front of the function body, and now we have an expression, which is this one. This expression does not need any variables defined outside it, and it represents the sequence with no premises. That's the same thing. So no premises in the sequence means this expression does not need any values defined outside it. So that's it. The Scala code is exactly this. This is the entire Scala code of this function. So in this way, we see that any expression in the code has a type that we can translate into the sequence by putting to the left of the turnstile as a premise anything that this expression uses that has already been computed before, any variables of types that are computed before. To the right of the turnstile in the sequence, we put the type of the entire expression. So in this way, we translate any expression from code into a sequence. And then, if we find a proof of the sequence using the axioms and derivation rules, then we can directly translate every step of the proof into code. Every step of the proof becomes some kind of combination of code expressions. And we have a table, or we could compile a table that gives us a correspondence between each axiom or derivation rule in terms of sequence and the code expressions and the ways of combining them that these axioms and derivations rules came from. So by construction, the axioms and derivation rules in this logic are precisely those for which we have some code expressions. So there cannot be any proof that is untranslatable into code, as long as we use the right rules and axioms of the logic. And it's much easier to reason about logic than to reason about code expressions, because there is less information in the logic. We have discarded all the specific computations that are in the code, and we only keep the types. And so there is less to reason about and more clarity, therefore, as long as we only look at type information. So we can temporarily forget that this came from some code. We just look at the rules of logic and follow the derivations and find proofs purely manipulating symbols in the logic. So that is faster, and that is the hope of getting some results. At the end, we will translate that into code. And we know we can always do that because each step in the proof initially came from a specific type of code expression or construction that we have in our programming language. So, and we know this is true for any programming language that adheres to this paradigm. OCaml, Haskell, Scala, Swift, F#, Rust, and several others. So let us see what we have achieved. So basically any theorem of logic, that is, any statement that can be derived in the logic, corresponds to some code that we have written. So here are some examples. This is a theorem of logic. For all A, if A is true, then A is true. Maybe not a very interesting theorem, but this is just a simple example. And then we can write code in Scala like this. It takes an argument of type A and returns the same value. Take a value of type A, return unit. No problem, we can do that too. Just ignore this argument, return unit. Take an A, return a value of the disjunction type. That's easy. We just take a left of x. And we get a value of the disjunction type. Similarly, for taking the first value out of a tuple, that's just using this. And this example we just saw how to derive that. In Scala we could write it like this, for example, one of the ways of writing it. Another way we're showing here. This is equivalent in Scala, just different syntax. Importantly, non-theorems cannot be implemented in code. So non-theorems are statements in logic that cannot be derived. Statements that are false or underivable. Examples of these statements are these. For all A, from 1 follows A. Now, this is certainly suspicious in terms of logic. What if A were false? Then we would have that from true follows false. That's very obviously wrong. And we cannot implement a function of this type. To implement it, we would have to take a unit argument and produce a value of type A, where A is arbitrary type. But how can we produce a value of type A, of a type that we don't even know what it is? And there is no data for us to produce that value. So it is impossible. Another example of an impossible type is this type. So from A plus B follows A. If you wanted to implement this function, you would have to take a value of disjunction type, A plus B, and return a value of type A. But how can you do that? What if the disjunction type happens to contain B and no A, just B? It cannot contain A if it contains a B, it's a disjunction. So then we don't have an A, and then we again cannot produce an A. And having a B, which is a completely different arbitrary type, doesn't help us to produce an A. Exactly the same reason shows why we cannot produce an A and B given A, because that requires a B that we cannot produce. And also this is not implementable, because we are required to produce an A, but all we have is a function from A to B. This function will consume an A if given an A. This function cannot possibly produce an A for us. But we are required to produce an A as a result, so we cannot. And also there is no proof of this formula in the logic. So these examples actually lead us to a natural question. How can we decide, given a certain formula, whether it is a theorem in logic, and therefore whether it can be implemented in code? It is not obvious. Consider this example. Can we write a function with this type in Scala? It is not obvious. Can we prove this formula? It is not clear. Not quite obvious right now. Suppose I were of the opinion that this cannot be proved. But how do I show that this cannot be proved? I certainly cannot just try all possible proofs. That would be infinitely many possible proofs. That would give me all kinds of other formulas, and that would give me nothing that I can stand on. how to answer these questions. So it is really a very hard question. We are not going to try to answer it on our own. We are going to use the results of mathematicians. They have studied these questions for many, many years, for centuries. Logic has been studied since ancient Greece, more than 2,000 years of study. All we need to do is to find out by what name mathematicians call this logic. They have probably already studied it. What kind of logic is this that we are using, that follows from the type constructions? Remember, at the very beginning of our consideration, we started with the type constructions that our programming languages have. So that set of type constructions specifies the set of rules of derivation of the logic. Mathematicians call this logic intuitionistic propositional logic, or IPL. Also, they call it constructive propositional logic, but it is less frequently used. The most frequently used name is this. And mathematicians also call this a non-classical logic because this logic is actually different from the Boolean logic that we're familiar with, the logic of the values true and false and their truth tables. I assume that you're familiar with those computations using truth tables and operations and or not in the Boolean logic. So actually, this logic, the logic of types, as I call it, or intuitionistic propositional logic, is very different from Boolean logic in certain ways. It's similar in other ways. Disjunction, for instance, works very differently. Here's an example. Consider this sequent. If it is given that from A follows B plus C, then either from A follows B or from A follows C. It sounds right from a common sense point of view. If B plus C follows, B or C follows, I'm using plus as a logical or. So if B or C follows, then it kind of makes sense that either B follows or C follows. Indeed, this is correct in the Boolean logic, which we can find out by writing the truth table. So we enumerate all the possibilities for A, B, and C to be true or false. There are 8 such possibilities. And for each of those possibilities, we write the truth value of this, the truth value of this, and we see from the table that whenever this is true, then this is also true in the Boolean logic. But this does not hold in the intuitionistic logic, or the logic of types. Well, why does it not hold? That's counterintuitive. Well, in fact, there is very little that's intuitive about this so-called intuitionistic logic. Actually, we need to think differently about this logic. We need to think, can we implement an expression of this sequent? So implementing it would mean, if we're given this expression, we can build an expression of this type. So if we're given an expression of type A to B plus C, let's say some f of this type, can we build an expression of this type? We can ask this differently by asking, can we implement a function that takes this as an argument and returns this? Well, we know that this is equivalent. One of our derivation rules is that if you have this sequent, then you can also have the sequent that is a function type from this to this. So for the programmer, it is easier to reason about a function, taking this as an argument and returning this. So how can we implement this function? This function takes f and needs to return a value of this type. So the body of this function, if we could implement it, would have to construct a value of type either of something. There are only two ways of constructing a value of type either. One is to construct the left value. Second is to construct the right value. How do we decide whether to construct the left value or the right value? We have to decide it somehow. On the basis of what information can we decide it? We don't actually have any such information. What we have here is a function from A to either B, C. So given some value of A, of type A, we could compute f of that value, and then we would have either B or C. We could decide then whether to, we could take then that B or that C, but that's not what we need to return. We don't need to return either of B, C. We need to return either of this function or that function. And that function is not yet applied to any A. It is too late for us to ask what is the A. We already have to return a left of this or a right of that. In other words, this type, either of something something, is not itself a function of A. It contains functions of A, but itself it cannot be decided on the basis of any A's. It's too late. So we need to supply a left or a right. So here, right away, immediately we have to decide whether this will return a left or a right. And we cannot really decide that. If we decide we return a left, we must then return a function from A to B. But there's no way for us to construct this function if we're given this function, because this function could sometimes return C instead of B, and then we'll be stuck. We cannot do this. And we cannot also return the right either. So it is impossible to implement a function of this type. Implication also works a little differently in the intuitionistic logic. Here's an example. This holds in Boolean logic, but not in intuitionistic logic. Again, let's see why. How can we compute this, given this? This function will give us an A only when given an argument of this type. But how can we produce a value of this type? We cannot. We don't have information that will allow us to produce a value of this type. A and B are some arbitrary types. Remember, there is universal quantifier outside of all this. For all A and for all B, we're supposed to produce this, and that is impossible. We don't have enough data to produce some value of type A, and so we cannot implement this function. Conjunction works kind of the same as in Boolean logic. So here's an example. This can be implemented, and this is also in Boolean logic a true theorem. Now, in Boolean logic, the usual way of deciding whether something is true or something is a theorem is to write a truth table. Unfortunately, the intuitionistic logic cannot have a truth table. It cannot have a fixed number of truth values, even if you allow more than 2 truth values, such that the validity of formulas, the truth of theorems, can be decided on the basis of a truth table. This was shown by Gödel, and this means we should not actually try to reason about this logic using truth values. It is not very useful. Even an infinite number of truth values will not help. Instead, however, it turns out that this logic has a decision procedure or an algorithm, and this algorithm is guaranteed either to find a proof for any given formula of the intuitionistic logic, or to determine that there is no proof for that formula. The algorithm can also find several inequivalent proofs if there is a theorem. So a theorem could have several inequivalent proofs, And since each proof could be automatically translated into code of that type, it means we could generate several inequivalent expressions of some type sometimes. So that is the situation with this logic, which we discover if we read papers about intuitionistic propositional logic that are available in the literature. And there are open source projects on the web, such as the GinGHC, which is a compiler plugin for Haskell. This is another project doing the same thing. And for Scala, I implemented the Curry-Howard library. Both of these Scala and Haskell, all of these Scala and Haskell projects do the same thing. They take the type of some expression or function and generate code for it automatically by translating the type into sequence, finding a proof in this logic using the algorithm, and translating that proof back into code in the way that we have seen in an example. It is interesting that all these provers, and there's a few others, there's one more for the Idris language that I did not mention here, they all use the same decision procedure or the same basic algorithm, which is called LJT, which was explained in a paper by Dickhoff here. They all cite the same paper, and I believe this is so because most other papers on this subject are unreadable to non-specialists. They are written in a very complicated way, or they describe algorithms that are too complicated. So I will show how this works in the rest of this tutorial. In order to find out how to get an algorithm, we need to ask, well, first of all, do we have the rules of derivation that allow us to create an algorithm already? Here's a summary of the axioms and the rules of derivation that we have found so far. These are direct translations of the code expressions that we had in the programming language in the notation of sequence. Now, there's one other notation for derivation rules, which looks like a fraction, like this. The numerator is one or more sequence, and the denominator is a sequent. And this notation means, in order to derive what is in the denominator, you have to present proofs for what is in the numerator. So this is the convention in the literature. This fraction-like syntax or notation. Now, we keep in mind that proofs of sequence are actually just code expressions that have these types as some variables and this type as the entire expression. So these are directly corresponding to proofs of these sequence and to the proofs of these derivation rules. And so if we have a proof that operates by combining some of these axioms and some of these derivation rules, we directly translate that back into code. Now, the question is, do these rules give us an algorithm for finding a proof? The answer is no. How can we use these rules to obtain an algorithm? Well, suppose we need to prove some sequent like this. In order to prove it, we could first see if the sequent is one of the axioms. If so, then we have already proved it. We know what expression to write. Okay. Now, in this case, none of the axioms match this. So match means maybe A is A times B, so B here is C, and then on the left we must have C or we must have A times B. No, we don't. We don't have C on the left as a premise. We have B plus C, but that's not the same. We also don't have A times B as a premise. We have A, but we don't have A times B. So these rules don't match. The other rules don't match the premises and the goal either. And also these rules, so how can we use them? Well, on the right there must be an implication. We don't have an implication on the right. Here we could try to delete some of the premises because it's unused. Well, actually, it doesn't look like a good idea. We delete A, for example, and we end up with a really hopeless sequence. From B plus C, we cannot get an A ever. And so that sounds hopeless. So this doesn't seem to help. And changing the order doesn't seem to help much either. And so we cannot find matching rules, but actually this sequence is provable. Just a clever combination of what axiom to start with and what rule to use, and then again some axiom and so on. It will give us that, I'm sure, because I know how to write code for this. This is not difficult. You have a function with two arguments. One of them is A, the other is B plus C, so disjunction of either B, C. And we are supposed to produce a disjunction of tuple AB or C. That's easy. Look at this disjunction. If we have a B in this disjunction, then we can produce a left of the tuple AB, because we always have an A anyway. If we have a C in this disjunction, then we could return this part of the disjunction, the right of C, and we're done. But unfortunately, we see that the rules here do not give us an algorithm for deciding this. We need a better formulation of the logic. Again, mathematicians need to save us from this situation, and they have done so. Mathematicians have studied this logic for a long time, starting from the early 20th of the last century. The first algorithmic formulation of the logic that was found is due to Gentzen, who published what he called a calculus. Just ignore the word calculus, it means not very much. Complete and sound calculus means that he came up with some rules of derivation, which are summarized here, such that they are equivalent to these. They derive all the same theorems and only the same theorems. So they derive all the stuff that is right and only that stuff. They don't derive any wrong statements. It's very hard to come up with such a system of axioms and derivation rules that are equivalent to another one in this sense. Also, it's very hard to prove that these are actually the rules that will give you all the theorems that could be right in this logic, that you can actually derive all the theorems that are right. That work is already done by mathematicians, so we're not going to try to do it ourselves. We're just going to understand how these rules work. Now, the syntax here is slightly enhanced compared with this. And the enhancement is that there are names for each rule. Now, these are just labels. They don't really do anything in terms of sequence. These help us identify which rule has been applied to which sequent. And that's all they do. So, other than that, it is the same notation. So, the fraction, such as this one, means that there is a sequent in the denominator, which we will prove if there are proofs given for sequence in the numerator. In this rule, there are two sequents in the numerator. Other rules may have one sequent in the numerator or no sequence in the numerator. So these rules that have no previous sequence required, those are axioms. And this axiom means if you have an atomic x, in other words, it's a variable, it's a type variable, it's not a complicated expression, just a type variable, then you can derive that same variable. This is our axiom right here. Now, why is it important that this is atomic, that this is a type variable and not a more complicated expression? Actually not important, but it's the simplest rule that you can come up with. And mathematicians always like the most minimal set of rules. So that's why they say, let's only consider this rule for the type variables x and not for more complicated expressions. But we can consider this rule for any expression, of course. The identity axiom. And here's the truth axiom, which derives the truth, which is this T symbol, which I denoted by 1 before, but in the logical notation this is the T symbol. Well, let's just call this 1 for clarity. So that can be derived from any premises with no previous sequence necessary. And then there are these other rules. Now, what do these other rules do? They do an interesting thing, actually. Each of these rules is either about something in the sequent on the left to the turnstile, or something in the sequent to the right of the turnstile, which I here shown in blue. So these are the interesting parts of the sequent that are being worked on or transformed by the rule. So here's an example. This rule is actually two rules. The I is the index, so I is 1 or 2. There are two rules, just written for brevity like this, with index I. And each of them says, you will prove this if you prove this. So for example, you will prove C given, if you're given A1 and A2, if you will prove C given just A1. Which makes sense, because if you can prove C given A1, you don't need A2. You can ignore this A2, you can already prove C from A1. So in this way, it would be proved. And so all these rules work in this way. You can prove what's on the bottom of the fraction if you're given proofs for what's on the top. So these are 8 derivation rules and 2 axioms. We can use this now to make a proof search. How do we do that? We start with a sequent. We see which rule matches that sequent. So the sequent must have something on the left and something on the right. Well, at least one of these. It cannot be empty. So it must be something somewhere. And there are only 4 kinds of expressions in our logic. Type variables, conjunctions, implications, and disjunctions. Now, notice I'm using this arithmetical notation for logic just because I like it better, and I will show that it has advantages later. So we take a sequence, we see which rule matches. One of them will match, because either in the premise we have one of these expressions, or in the goal we have one of these expressions. And then we find the rule that matches, we apply that rule, so we now have new sequence, one or more, that would need to be proved. And if there are 2, then we fork the tree, and now we have to prove both of them. So we continue doing that for each of the sequence until we hit axioms. So the tree will end at this leaf, or we hit a sequence to which no rule applies, in which case we cannot prove it and the entire thing is unprovable. So in the search tree, there will be sequence at the nodes of the tree, and proofs will be at the edges of the tree. So each node sends its proof to the root of the tree. This calculus is guaranteed by mathematicians to be such that indeed, if you cannot find a rule that applies, it means the sequent cannot be proved, which was not the case here. The sequent can be proved, and yet we cannot find a rule that applies. So in this calculus, we can use bottom-up approach to make a proof search as a tree. Here we cannot. That is the advantage of capitalizing on the mathematician's results. Let us look at an example. Suppose we want to prove this formula, this theorem. So first step, we need to write a sequent, and this needs to be proved from no premises. So we write a sequent S0, which has an empty set of premises, and this is as a goal. Now, what rule applies to this sequent? We do bottom up. So, in other words, we look at these rules and we find which denominator matches our sequent. Well, in our sequent there is empty set on the left, so all of the rules on the left cannot be applied to it. But on the right, we have an expression which is an implication. At the top level of this expression, there is this implies that. So this is of the form A implies B. So this rule applies. We have a sequent of the form something, in our case this is an empty set, and then A implies B. So we apply this rule, which is the right implication, and we get a new sequent, which is that what was here before the implication is now put on the left to the left of the turnstile, and it means that this expression needs to be now to the left of the turnstile. So now this is the sequent S1. Now we need to prove S1. We see what rule applies to S1. Well, on the right there is just Q, so nothing can be done with these rules. And Q is not truth, so we cannot use the axiom either. So let's look at the left rules. On the left we have now an implication. So this is, let's say, A, and this is B. So we have a rule which has A implication B on the left. This is the rule left implication. Let's apply it. That rule will give us two new sequents. So these two new sequents are S2 and S3. There are these sequents, as you can check. If you match A implication B against this implication Q, so this is A, this is B. So then you get these two sequences. Now we have to prove these two sequences, S2 and S3. S3 is easy, it is just the axiom of identity. It is this. Now S2 again has an implication on the left. Let's again apply the rule left implication to that. We get two more sequences, S4 and S5. S4 is this, and S5 is this. So now actually we are in trouble, because S2 and S4 are the same sequent. S5 actually we could prove with some more work, but that won't help, because we are in a situation when to prove S2 we need to prove again S2. So that's a loop. That will never give us anything. It means we applied the wrong rule. So we need to backtrack this step. When we apply the rule left implication to S2, we erase S4 and S5 and try a different rule to apply to S2. Which rule can apply to S2? Well, S2 is this. It actually has implication on the right. So we can use the right implication rule. And if we do that, we get a sequence S6, which is this, And this sequence immediately follows from the identity axiom, because it has premise R on the left and premise R and goal R on the right, and that is this axiom. Whatever other premises, and then premise X on the left, premise X on the right, and that is a type variable, so that's perfect. We have done the proof. S6 follows from the axiom, and therefore we have proved S0. No more sequence need to be proved. And because sequent S0 shows this to be derived from no premises, then this formula is the theorem. That's what the theorem means in the logic. So that is how we use this calculus to do proof search. Now, we notice that we were a bit stuck at some point. We had a loop. Now, if we are in a loop, we don't know what to do. Maybe we need to continue applying the same rule. Maybe some new sequence come up. Or maybe we should not continue. It is not clear what to do. And just looking at the rule left implication shows us that it's copying this premise, the A implication B, it is copied into the premises of the new sequent, and so it will generate a loop assuredly after the second time you apply it. However, this sequent might be new, so we might need to apply it second time. We don't know that, so that is a problem. It will loop. Now, there have been a lot of work trying to fix this problem, and literally decades of research by mathematicians. The main ones I found were Vorobyov, who published in the Soviet Union, Hudelmeier and Dickhoff, who published in the United States over this time, discovered gradually a new set of rules, which is called LJT, or the calculus LJT, which cures this problem of looping. The way it cures this problem is by replacing this rule, left implication, through 4 new rules, which are listed here. All other rules are kept the same from this calculus, except the rule left implication, which is replaced. In what way? So left implication was applied to a sequent when the sequent had an implication among the premises, or on the left, to the left of the turnstile. The new rules look in more detail at what is that implication. So that implication could have one of the 4 expressions as the argument of the implication. It could have an atomic expression as the argument. It could have a conjunction as the argument. It could have a disjunction as the argument. Or it could have an implication as the argument. In our logic, there are no more expressions except these 4: atomic variables, conjunctions, disjunctions, and implications. And so we have here enumerated all the possibilities for what could be to the left of the implication in this premise, which I have here shown in blue. And so for each of these we do certain things, replacing these sequence with one or more other sequence. Again, it's quite a lot of work to prove that these rules are equivalent to these, and also that the new rules are somehow better. They are not giving loops. A lot of work which I'm not going to go through because that's far too complicated for the scope of what we need. Suffice it to say that we have very smart people who published on this, and it is reasonably sure that this is correct. So the T in the name LJT stands for terminating. So if we use these rules in the same way by creating a proof tree, the proof tree will have no loops and it will terminate after a finite number of steps. And there is actually this paper that is also helpful for understanding how to implement this algorithm. And this paper shows explicitly how to construct an integer function from sequence to integers, which is a measure of the complexity of the sequent, and this measure decreases every time you apply a rule. So it strictly decreases. And since this is a strictly decreasing measure on the proof tree, it means that all the next nodes in the proof tree will have a smaller value of this measure, so eventually it will hit 0 and the proof tree will terminate at that leaf. Either that or you have no more rules to apply. And if you have no more rules to apply, then again, mathematicians have proved it means our sequent cannot be proved. So this is an important result that we are going to use. And note that this rule is quite complicated. It does a very interesting thing. It takes this expression, which has implication inside an implication, and it transforms this expression in a weird way. Namely, the b here is separated from the c by parentheses, but here it is not separated. So this transformation is highly non-trivial and unexpected, and its validity is based on this theorem that this in the intuitionistic logic is equivalent to this. Equivalent means they're both following from the other. So from this follows that, and from that follows this. So this key theorem was attributed to Vorobyov by Dikhoff in his paper. And this is this lemma 2, which says that if this this derivation is if and only if that derivation, so there are these two equivalences, and the proof is trivial, and the 34 is a reference to Vorobyov. Now, when a mathematician says that something is trivial, it doesn't mean that the statement is easy to understand. It doesn't mean that the proof is easy to find, or that it is easy to understand. It means none of these things. It just means that right now, for this mathematician, it is not interesting to talk about how it is done. That's all it means. Could be for any number of reasons. For example, mathematicians could just be lazy or have no time to, again, explain this, and so they say it's trivial. Don't be deceived when you see somebody says that something is trivial in a mathematical text. So to prove this, one stepping stone could be to prove this first. This is an easier theorem. And if you prove this, then clearly from here you can get b to c. B to c you can substitute in here, you can get a to b, and then you have here a to b. So in this way you can show this equivalence in one direction. Now the proof of this statement is obviously trivial. In order to show the expression of this type, I will use my short notation. So this is f, which has this type, the first argument of the function. The second is b, which is of this type. And then we need to produce a c. How do we produce a c? We apply f to an argument of this type. The argument of this type is a function that takes a and returns a b. So we take some x of type a, and we return a b, which was this b. So we ignore this x, we just return that b. And that's the argument of f. So this expression is the proof of this sequent. In other words, this is the code that has this type, and therefore the proof must be available somehow. So the details of proving this theorem are left as an exercise for the reader. Again, when you see in a mathematical text that something is left as an exercise for the reader, it does not mean that it is easy to do. It does not mean that for you it would be a useful exercise to do. It also does not mean that the author knows how to do it. It means none of these things. It just means the author doesn't feel like doing it right now and showing it to you for whatever reason. Could be because they're lazy, could be because they don't know how to do it, could be because they feel that they should know how to do it, but they don't really know how to do it. Could be any of these reasons. Don't be deceived when you see something like this. But of course I had to actually produce an expression, a function of this type in order to implement my Curry-Howard library, because as I will show in a moment, you need to be able to implement all these as code in order to have a prover. So why is that? We believe, the mathematicians, that the new rules are equivalent to the old rules. Which means that if you find a proof using these rules, somehow you should be able to find a proof also using our initial rules, which means that if you found that proof, you would easily translate that to code, because each step here is directly corresponding to a certain code expression, as we have seen at the beginning of this tutorial, these code expressions for each of these operations. So, in order to do this with new rules, in other words, in order to create code from proof using new rules, we need to show equivalence, or we need to show how to get code out of each of the new rules. Now, proof of a sequent means that we have some expression, let's say t, that uses variables a, b, and c of these types, and the expression itself has type g. And also, as I have shown, this could be conveniently seen as a function, the t as a function from a, b, and c, from these three arguments, to the type g. So, for each sequent in a proof, we should be able to show either that it follows from an axiom, one of these, or that it follows from a derivation rule. And a derivation rule transforms one proof into another. The axioms are just fixed expressions, as we had before. The axioms actually didn't change between our initial formulation of the logic and the new calculus LGT. They actually did not change. The derivation rules changed, and each new derivation rule means that you're given expressions that prove the sequence in the numerator, one or more, and you, out of these expressions, somehow you have to construct an expression that proves this sequent. Now, when I say an expression proves the sequent, what it means is that the expression has the type that is described by the sequent. It's the same thing, because we described types of expressions through sequence, and only those sequence that correspond to valid and existing expressions in the programming language, only those sequence can be proved by the logic. This is by construction. So now we need to just find what are these expressions that correspond to each of the derivation rules. And each rule has a proof transformer function, as I call it. And the proof transformer function is explicitly a function that takes one or more expressions that are in the numerator and converts that to the expression in the denominator that has this type. So it has an expression of has an explicit function that we need to write down for each of the derivation rules. So let's see how this is done for these two examples of derivation rules. First example, we have a rule that says if you want to derive this sequence, you need to derive these two sequents. Now, this sequence represents an expression of type C, which uses an expression of type A plus B. So let's represent this as a function from A plus B to C. Now, we will, for brevity, just ignore these other premises, which are common arguments in all these functions. We just pass them and we don't write them out. What is the proof transformer for this derivation rule? The proof transformer for it is a function that has two arguments, t1, which is the proof of this, which must be a function of type A to C, and t2, which is a proof of this sequence, which must be a function of type B to C. Now, earlier I said that sequence represent expressions that use certain variables, but equivalently we can say these are functions that take these variables and return these expressions. That's more convenient when you implement this in code. So what we need is a function that takes A to C and B to C and returns a function from A plus B to C. And this is the code that does it. We take an argument of type A plus B and we return a match expression. If it's in the left, we apply t1 to that value and we get a C. If it's in the right, we apply t2 to that value and we get a C. So in any case, we get a C out of this. So this is a function from A plus B to C as required. Another example is the proof transformer for this rule. This rule has one sequent going to one sequent. So in order to transform this proof into this, we need a function that takes argument of type A to B to C to D and returns a function of type tuple AB going to C to D. So here's the code. We take a function f of type A to B to C to D. We return a function that takes a g of this type, shown here in blue, and we need to return a d. So how do we get a d? We apply f to a function of type A to B to C. So we create that function out of g. How? X of type A going to y of type B going to g of xy. So this is a function of type A to B to C, which is the argument of f as required. And the result is of type D. So that is what we write. So this kind of code is the proof transformer for this derivation rule. And we need to produce these proof transformers for every rule of the calculus LJT. And I have done it, because I have implemented the Curry-Howard library that uses LJT. So I must have done it for each rule. This is a bit tedious because there are many of those rules, and you need to implement all this machinery of passing arguments, no matter how many, in this gamma, which I omitted from this notation for brevity. But of course, in the real code, you have to deal with all that too. So let's see how this works on an example. Because once the proof tree is found, we need to start backwards from the leaves of the tree back to the root. On each step, we take the proof expression, apply the proof transformer to it according to the rule that was used on that step. We get a new proof expression and so on. So for each sequence, we will get a proof expression, and at the end we will have a proof expression for the root sequence, and that will be the answer. So I will denote by ti the proof expressions for the sequence Si. So starting from S6. S6 was this sequence in our proof. So I'm just going through the proof example that was here, backwards from S6 back to S0. S6 was this. It followed from axiom identity. Its proof expression, T6, is a function of two variables. These two variables of these two types. And this function just returns the second variable. So it's a function of RRQ and R. I just denoted this by RRQ. The variable of this type is RRQ. The variable of this type is R here. So this function is very simple. It just ignores the first argument and returns R. So that is what the axiom does. The next sequence was S2. S2 was obtained by rule R implication or right implication from S6. So the proof transformer for right implication, let's look at the right implication and see what the proof transformer must be. So we are given this sequence for this expression, which is the function body. The function body that uses a variable of type A somehow. Out of this, we need to produce a function expression that takes an argument of type A and returns that function body. So this is the code, which is just writing a new argument, returning the function body. That was our proof transformer. We need to convert function body into a function. So we just write that argument and arrow and the function body. So in our case, we need this as a function body. And so our T2 is a function of RRQ, and this function is this. The sequence S3 followed from the axiom, and so it was just this function. T3 is just the identity function. Then we used the rule left implication. So this was actually still done in the calculus LJ, but the same thing works in the calculus LJT. I'm just using LJ because it's simpler. For example here. Proof transformer for the left implication is a little more complicated. And so if you look at it, what does it have to be? It takes these two expressions and returns this expression. So it takes a function from A to B to A and from B to C, and it returns a function from A to B to C. How does it do it? Given a function A to B, you use this to derive A from it. Then you substitute that A into the function A to B, you get a B. Then you use this to derive C from that B, and that's your C. So you use this function A to B twice. You put it in here once, and then you get an A, and then you substitute back into the same function, and you get a B, and then you use that. And that's exactly what the proof transformer does. It takes this RRQ, and it uses it twice. Substitutes into it something that was obtained from one of the terms, and then uses the second term on the result. So then this is the proof transformer for the rule left implication. The result of the proof transformation is the proof for the sequence S1. Finally, we use the right implication again, which is just this function construction, and we get the proof expression for the sequence S0. Now, this proof expression is written through these T1, T2, T3. We have to substitute all of this back in order to get the final expression. So if we substitute, first of all, we find this is RRQ going to T1 of RRQ. T1 of RRQ is this, so we have to put it here. Now T3 is just identity, so we can just remove that. So that gets you RRQ going to RRQ of T2. T2 is this, so you have to put it in. T6 is just identity on R, so this is R going to R, and so finally you have this expression. So that is the final code that has the required type. Notice that we have derived this code completely algorithmically. There was no guessing. We found which rules applied to the sequence. We transformed sequence according to the rules. Once we found the proof, which was, if we use the calculus LJT, the proof will be just a finite tree with no loops. It will terminate. You can get an exhaustive depth-first search for it, for example, and you find all the possible proofs if you want as well. Well, you will find many in any case in some for some expressions. And then we use the proof transformers, which are fixed functions that you can upfront compute for each rule. So these expressions are proof transformers applied to the previous proofs. So these are completely fixed, algorithmically fixed. So we have derived this code completely algorithmically given this expression, this type. So it is in this way that the Curry-Howard correspondence allows us to derive the code of functions from their type signatures. Another important application of the Curry-Howard correspondence is to analyze type isomorphisms or type equivalences. And I was led to this by asking the question, so in this logic, or in the types, are these operations plus and times, as I denoted them, more like logic, more like the disjunction and conjunction, or are they more like arithmetic plus and times? Because this is kind of not so clear right away. Our logic is this intuitionistic logic. In any case, this is different from Boolean logic. So what are the properties of these types, really? So are the properties such that it is better to think about these operations as plus and times rather than logical conjunction and disjunction? To answer this question, I looked at identities that we have in the logic. These are some identities, from simple ones, obvious ones, to less obvious identities like these. The equals sign here stands for implication in both directions. So both this implies that and vice versa. Because of this, each of the implications means a function. So since these are all identities in logic, it means that, for example, the implication from here to here is a theorem of logic, and so it can be implemented. As we know, all identities in logic can be implemented in code, and we even have an algorithm now that can automatically produce proofs and automatically produce code. So that means for any of these identities that has some expression x on the left and some y on the right, so some kind of x equals y, we have x implies y and y implies x. If we convert that to code, we will have a pair of functions, a function from x to y and a function from y to x. What do these functions do? Well, they convert values in some way from type x to type y and back. So do these functions express the equivalence of the types x and y, so that any value of type x can be converted to some equivalent value in type y and back without any loss of information? Is that so? That was the question I asked. I looked at some examples. Well, first, what does it mean more rigorously that types are equivalent, or as mathematicians say, isomorphic? The types are isomorphic, and we will use this notation. for that. If there is a one-to-one correspondence between the sets of values of these types. And in order to demonstrate that, we need a pair of functions, one going from A to B, the other going from B to A, such that the composition of these functions in both directions is equal to identity function. So f compose g, or f then g, will give you from A to B and then from B to A back. So that would be identity of A to A. This will be identity of B to B. If this is true, if the composition is identity, it means we indeed did not lose any information. Let's consider an example. This is an identity in the logic. A conjunction with 1 is equal to A. In Scala, the types corresponding to the left and the right-hand sides of this conjunction, or of this equivalence, are the conjunction of A and unit, and A itself. Now we need functions with these types. Indeed, we can write functions easily having these types. A pair of A and unit, we need to produce an A out of that. Well, just take the first element of the pair, you're done. Take an X of type A, we produce a tuple of A and unit. Very easy, just put a unit value in the tuple and you're done. And it's easy to verify that composition of these functions will not change any values. So it will be identity in both directions. Another example. This is an identity in logic if this is understood as a disjunction. 1 or A, or true or A, is true. That is an identity in the logic, or theorem in the logic. Are the types equivalent, though? The type for 1 plus A is the option. In Scala it is option, in Haskell it is called maybe. This type is standard library type in pretty much every functional programming language. Now, option of A is a disjunction of 1 or unit and A. It is certainly not equivalent to just unit, because this type could contain a value of A in it, but this could not. So there's no way that you could transform this type to this and then back without losing information. You could transform. So since this is a theorem, you have functions from this type to this type and back. Some functions, you have them. But these functions do not compose to identity. They cannot. Because what if you had A here? You must map it into unit. From this unit back, you must map into this unit. You cannot get an A out of unit. And so that will erase this information, and that cannot become isomorphism. So we see that some logic identities do yield isomorphisms of types, but others do not. Why is that? Let's look at some more examples to figure out why. In all these examples, we can implement functions f1 and f2 between the two types in both directions. And then we can check, we certainly can implement them because these are logical identities, but then we can check if the compositions are identity functions. And if so, the types are isomorphic. But we find that in the first three examples we can do it, but in this last example we cannot. Now I have written the logical identities or logical theorems with the arithmetic notation. I call this arithmetical notation because this suggests arithmetical operations, plus and times. And if you look at these identities, this looks like a well-known algebraic identity from the school algebra. And this too. But this certainly seems wrong as an arithmetic, as an arithmetical identity. This is certainly not true in arithmetic. It is true in logic, though. If you replace this with disjunction and this with conjunction, this is an identity in logic. So this suggests an interesting thing. If you replace disjunction by plus and conjunction by times, and the result is an identity in arithmetic, then it is an isomorphism of types. Otherwise, it is not. Let's see why this is so. Indeed, this is so. I call this the arithmetical Curry-Howard correspondence. To see how it works, let's consider only the types without loss of generality that have a finite set of possible values. For example, a Boolean type has only two possible values, true and false. Integer, let's say in the computers, all the integers are finite, so those types have a finite set of possible values. And this does not limit our generality, because in the computer everything is finite. All types have a finite set of possible values. Now let's consider how many values a given type has. So that would be the size of the type, or using the mathematical terminology, it's called the cardinality of the type. So let's see what is the cardinality of various type constructions. The sum type, for example, if the cardinality of types A and B is known, then the cardinality of A plus B, the sum type, the disjunction of A and B, is the sum of the two cardinalities or sizes. This is because a value of the disjunction type is constructed as either a value of the first part or a value of the second part, and so you cannot have both together. And so obviously the different number of values is just the sum of the two sizes. The number of different values of the sum type is just the sum of the numbers of different values of types A and B. For the product type, again we have an interesting thing. It's the arithmetic product of the sizes of A and B, because for every A value you could have an arbitrary B value. And so this is a direct product or Cartesian product of sets. And we have school-level identities about the operations plus and times, such as these identities, or these. All of these identities are valid for arithmetic, and they show, if you translate that into statements about the sizes of types, they show that the size of the type on the left is equal to the size of the type on the right. And that is very suggestive. In other words, if you take an identity like this, and you compute the size of the type on the left and the size of the type on the right, you get an arithmetic identity of the sizes. But you don't get that identity here, because the arithmetical formula is not right. This is very suggestive. If the sizes are equal, maybe the types are equivalent or isomorphic. When the sizes are not equal, then certainly they cannot be equivalent. The function type, very interestingly, also is described in the same way. It provides the set of all maps between the two sets of values. So, for example, from integer to Boolean, that would be all the functions that take some integer and return some Boolean. So that's the number of Boolean values to the power of the number of integer values. That's how many different functions you can have. That's a combinatorial number. So it's an exponential. And so the size of the type of function a to b is the size of the type of b to the power of the size of type of a. And again, we have all the school identities about powers and how to multiply powers and so on. And they are directly translated into these three identities. If you take the sizes of the types on the left and on the right, the sizes will be equal due to these three identities. since the sizes are equal, it's very likely that the types are actually equivalent. So far, haven't seen any counterexamples to this in these constructions. So this gives us a meaning of the Curry-Howard correspondence. So far, we have seen three facets of the Curry-Howard correspondence. One is the correspondence between types and logical formulas. Two is the correspondence between code and proofs. And three, the correspondence between the cardinality of a type, or the set size of a type, and the arithmetic identities that we have in the school algebra about these types. So arithmetical identities signify type equivalence or isomorphism, while logic identities only talk about how you create some value of this type out of value of another type. So that does not guarantee that it preserves information. It just guarantees that you can implement some function of that type. It doesn't tell you that the function will be an isomorphism. So if one type is logically equivalent to another, it means they're equally implementable. If one is implementable, another is also implementable. But no more than that. Whereas arithmetical identities actually tell you about isomorphism of types. Therefore, if you look at types and write them using my preferred notation, which is using the arithmetical symbols instead of logical symbols. So instead of these, I use these symbols. If I do that, this is very suggestive of a possible isomorphism of types. Then it becomes very easy for me to reason about types. I can see right away that these two are isomorphic types, or that these two are isomorphic types. Because I'm used to looking at school algebra, it's very obvious then that this is not an isomorphism of types, because this doesn't make sense in the school algebra. So reasoning about isomorphic types is basically school-level algebra involving polynomials and powers. So if you are familiar with all these identities, as you should be, it will be very easy for you to reason about what types are equivalent, as long as all these types are made up of constants or primitive types, disjunctions, tuples or conjunctions, and functions, which will then directly be translated into exponential polynomial expressions, constants, sums, products, and powers, or exponentials. So I call these exponential polynomial types, that is, types built up from these type constructions. So all we have been talking about in this tutorial is what I call exponential polynomial types. These are the basic type constructions that I started with: tuple, product, function, exponential, disjunction, sum, unit, constant, or one. Now, just one comment that in the functional programming community today, there is the terminology algebraic types. So people usually call algebraic types the types that are made from constant types, sums, and products, excluding exponentials. I do not find this terminology very helpful. I find it confusing, because what is particularly unalgebraic about these identities? These are identities of school algebra. The properties of the function type are described by algebraic identities like these. So it would be strange to call the function type not algebraic, whereas these types are algebraic. They are very similar to each other in terms of their properties being described by identities known from school algebra. So instead of algebraic types, I would prefer to say polynomial types. This is much more descriptive and precise. And if you want to talk about function types as well, then you can just say exponential polynomial types, or expoly types for short. So, by way of summarizing what we have done so far, what are the practical implications of the Curry-Howard correspondence? So one set of implications is actually for writing code and reasoning about code. One thing we can do now is, if we're given a function with some type, and usually this will be type with type parameters, all type parameters, fully parametric type, such as the function we have been considering here. All these functions do not have any types that are specific, like integer or string. All the types are fully parametric, and then there are some constructions, some type expressions made out of these types. So these are what I call fully parametric functions. For these functions, we have a decision procedure, an algorithm based on the LJT calculus, which decides whether this function can be implemented in code. And computer scientists say type is inhabited if you can produce a value of this type in your program. So CH of t is this proposition which they call type is inhabited. And I prefer to call it just that. You can compute a value of this type, or code has the type. Code can create a value of this type. And so we have an algorithm that can also generate the code from type when it is possible. If it is not possible, the algorithm will tell you so. Often, not always, but often, this algorithm can be used actually to generate the code you want. We can also use what I call the arithmetical Curry-Howard correspondence to reason about type isomorphisms and to transform types isomorphically, simplify type expressions, just like we simplify expressions in school-level algebra, by expanding brackets, by permuting the order of terms like a plus b is equal to b plus a, or associativity, a times b all times c can be expanded, and so on. So this allows us, once we have written types in the short notation, in the notation that I prefer, which resembles school algebra because it uses the plus and times symbols instead of the logic symbols. So once we rewrite our types in this notation, which I have been doing consistently in this tutorial, it enables us to reason very easily about which types are equal or isomorphic, because we are all familiar with the school-level algebra. What are the problems that we cannot solve using this knowledge? One thing we cannot do is to generate code automatically such that it will be an isomorphism. So, for instance, in an example here, we are able to generate automatically the code of these functions, but it will not be an isomorphism, and the LJT algorithm cannot check that this is an isomorphism. That's the important thing. This algorithm does not know about equations or isomorphisms. It only knows that it found some code that has the type you wanted. Whether this code is useful to you or not, we don't know. The algorithm doesn't know this. Also, if the algorithm finds several such several proofs of a sequence, it will generate several not inequivalent versions of your code. It doesn't know which one is useful. Maybe some of them are useless, maybe not. The algorithm cannot automatically decide that in general. Another thing we cannot do is to express complicated conditions via types, such as that array is sorted. The type system is not powerful enough in all the languages I listed. You need a much more powerful type system, such as that in the programming language Idris or Agda or Coq. Those are much more powerful type systems that can express such complicated conditions. But for those type systems, there is no algorithm that will generate code. Another thing we cannot do is to generate code that has type constructors, such as the map function. So here's an example. In Scala, this is a map function on a list. So there's the list of A. A is a type parameter. And then we say .map, and map has another type parameter, B. It takes a function from A to B for any B. So A is fixed, but now for any B, we can take a function from A to B and generate a list of B. So if we wrote this formula in the short type notation, this would look something like this. I'm writing subscript A because this is a type parameter, so this is like an argument or a type parameter. I'm writing it like this. And then from this is the first argument of the function, and then there's a second argument, which is this f, and that has another quantifier for b inside the parentheses. So this formula has a quantifier inside. So far we have been dealing with formulas that have all quantifiers outside, and so we never write quantifiers explicitly, but here we have to write them inside. This is a more powerful logic, which is called first order logic. In other words, this is a logic where you have quantifiers anywhere in the formula, including inside the formula. Unfortunately, this logic is undecidable, so there is no algorithm that we can use either to find a proof and therefore code for the type, or to show that there is no proof, no code. So we're kind of stuck in all these directions. Some more remarks about the Curry-Howard correspondence. First is that only with parameterized types we can get some interesting information out of it. If we take concrete types like integer, then the proposition ch of int, meaning that our code can have a value of type int, that's always true. We can always write some integer value. We don't need any previous data for it. So for all specific types, all these propositions are always true. It's completely void of information. The only interesting part comes when we start considering type variables. If we start asking, can we make a type which is either of AB going to A going to B and so on, for all AB. Once we start doing this with type parameters A, B, and so on, then we get interesting information, as we have seen in this tutorial. Another remark is that functions like this one are not sufficiently described by their type. So this is type of integer going to integer. Now, looking at this type, we can put this into a sequent, but we will never get enough information to actually get this function. So only certain class of functions, which are fully type parametric, their type signature is informative enough so that we can derive code automatically. Only in much more powerful type systems you can have type information that is enough to specify fully a code like this. Another caveat is that I don't know the proof that arithmetic identity guarantees the type equivalence. It is certainly a necessary condition, because if two types have different cardinality or different size of their sets of values, that they cannot be equivalent, or they cannot be isomorphic. So this is a necessary condition, but it's not a sufficient condition, it looks like. I don't know if this is sufficient. I haven't seen any counterexamples so far. Final remarks about type correspondence. The logical constant false did not appear in any of my slides so far. This was on purpose. It has extremely limited practical use in programming languages because actually we have types corresponding to false. Scala has type called nothing, and Haskell has type usually called void that corresponds to the logical constant false. What does it mean? Ch of nothing is false. It means your code can never have a value of type nothing, or in Haskell, void. You can never compute a value of this type. So clearly it has a very limited practical significance. You will never be able to compute any values of this type ever in any program. It's identically false, this constant. So if you want to add it to the logic, it's very easy. You just have one rule and you are done. You can derive things with it if you want, but they will have almost never any use in practical code. Also, we did not talk about the logical negation. None of the calculi that I showed had logical negation as an operation. Again, for the same reason. We do not have a programming language construction that represents logical negation. Negation, by definition, is like this, is an implication from A to false. So that's not A. Not A means from A follows falsehood. Now, since you cannot ever get false in a programming language, you cannot really implement this function in any useful sense. And so I have seen some Haskell library that used this type void as a type parameter in some way, but certainly it's a very limited and rare use. And so it is not really illuminating to include negation. You could probably find some very esoteric uses of it, but almost never useful. And finally, there is another set of important implications from the Curry-Howard correspondence. These are implications for people who want to design new programming languages. As we have seen, the Curry-Howard correspondence maps the type system of a programming language into a certain logical system where propositions follow from each other or can be proved from each other. And this enables us to reason about programs, to see what kind of code can be written if some other kind of code can be written. And logical reasoning is very powerful. It's simpler than trying to write code. And it gives you algorithms and all kinds of mathematical results that have been found over the centuries. So languages like those listed here have all the 5 type constructions that I listed in the beginning of this tutorial, and mapping them into logic gives a full constructive logic or full intuitionistic logic with all logical operations and or, so conjunction, disjunction, implication, and the truth constant. Whereas languages such as C, C++, Java, and C#, and so on, they're mapped to incomplete logics because they do not have some of these operations. For instance, they do not have type constructions that correspond to disjunction. They also do not have the true constant or the false constant. So they are mapped to a logic that lacks some of the foundational logical operations, so it can be only fewer theorems can be proved in that logic, and so your reasoning about your types is hampered. Languages called scripting languages sometimes, such as Python or JavaScript, Ruby, and so on. Also R belongs there, MATLAB. Those languages only have one type. They actually don't check types at compile time, and so they're mapped to logics with only one proposition. Those logics are extremely small in terms of what kind of things you can reason about, and so if you write a program in these languages, you're completely unable to reason at the level of types, whereas in these languages you are able to reason, but in a limited way. You're not having a complete logic. So this suggests a principle for designing the type system in a new programming language. The first step would be to choose a good and complete logic that is free of inconsistency. Mathematicians have studied all kinds of logics, and they are always interested in questions such as, is this logic consistent? Consistent means you cannot derive false from true. Is this logic complete? Can you derive all things that are true? Are there enough axioms and rules of derivation? Or maybe there are too many axioms and rules of derivation. You can delete some of them and have fewer. Mathematicians have always been interested in such questions. They found all kinds of interesting logics where you can derive a lot of interesting theorems, non-trivial theorems, and they found the minimal sets of axioms and rules of derivations for these logics. Use the results, take one of the logics that they developed, such as intuitionistic logic, modal logic, temporal logic, linear logic, and so on. Take one of these logics. For each of the basic operations of this logic, provide type constructions in your programming language that are easy to use. For instance, your logic has disjunction, implication, or something else. Provide a type constructor for each of them that's easy to use, easy to write down, such as provided by the languages we have seen. Then every type will be mapped to a logical formula. There will be a logical formula for every type, and there will be a type for every logical formula. And then for each rule of the logic, for each derivation rule, there should be a construct in the code that corresponds to it, so that you could transform proofs in the logic into code and code into proofs. If you do that, your language will be faithful to the Curry-Howard correspondence. You will be able to use logic to reason about your language. And one important result at this level, well, we have seen that you can sometimes generate code that is maybe nice, but a very important result is that if your logic is free of inconsistency, it means that no program will ever be able to derive an inconsistent type. An inconsistent type means that you had a function that requires some type A, but it was called with a different type B, which is incompatible, and that basically crashes. So in languages like C and C++, we have all kinds of crashes, like a segmentation fault. In Java, there are exceptions, null pointer exception, or class cast exception, which happens when you call a function on a wrong type of argument. And that happens if your logic is inconsistent. If your logic can derive incorrect statements from correct premises, then if you translate that derivation into code, then that code will derive incompatible type at the wrong place, and it will crash. The crash will happen at runtime. The compiler will not catch this inconsistency, because the compiler only checks the logic of types, and the logic checks out. You have followed the rules of derivation of the logic. The compiler can check out all these logical rules, but the compiler does not know that your logic is inconsistent, maybe, and then it will have derived an inconsistent result, falsehood from truth, for example, and that will crash at runtime. Now, we know that crashing at runtime is not a good outcome. So, in fact, languages like OCaml have been studied, or other languages, some subsets of Haskell, I believe called safe Haskell, have been studied, and it has been shown that they cannot crash. And the way to show it mathematically is to use the fact that they are based on a complete and consistent logic. And then all you need to show is that your compiler does not have some critical bugs that allow it to oversee that you have not followed the derivation rules of the logic. So that is an extremely valuable feature of functional programming languages that are based on the Curry-Howard correspondence. You can prove their safety at compile time, or at least exclude a large number of possible bugs and errors. Certainly, these languages are quite large, and they include features that are not covered by the Curry-Howard correspondence, type constructors that I have not considered in this tutorial, and those may not be safe, but at least the foundation of these languages the foundation of the type system will be safe. So that is the final lesson from the Curry-Howard correspondence. This concludes the tutorial.